Thank you so much for the introduction. Good afternoon, everyone. Before I get into that story, a big thanks to the organizers, the reviewers, and the session chair for having me here. It's been 2 days of amazing talks. Thanks again for that. Also, thanks to the judges of the poster presentation. We were awarded a poster on this was awarded the runner-up yesterday. So thanks again for that. The poster was made and presented by Sheng Rong. He's a PhD student at University at Houston, and he spent the summer in 2015 in our lab, and this is the result of that internship. So it was great that the travel award also worked out. So thanks for that. The topic, as you can see, is all about identifying lamp types. That is the type of the lamp that goes into your roadway street lights, right? Not really the topic that pops out as the hot topic in mobile computing. Nonetheless, I'll try to make the case that there is still some work left when it comes to our civic infrastructures like roads, utilities, and light poles. The previous speaker wanted to use potholes to make vehicle platooning safe. I'm cool with that too. But yeah, civic infrastructures in general need there's still some more work left to be done. A little bit of background on Philips Lighting Research. We are located in Cambridge. It's part of the Philips Lighting. The bulb people, the other labs are located in Eindhoven, which is where we are headquartered, and Shanghai and Bangalore. A little bit of digression. I was asked yesterday about if we hire interns. This is our class of interns in 2016. As you can see, Sheng Rong came back to spend a summer with us. So yes, we do hire interns. You can get in touch with me or go to the website. Coming back to the talk, the outline, I want to motivate this problem of lamp type identification. Why try to understand what are the lamp types in the poles, light poles? Give you a broad overview of our approach, get into a little bit of technical details, show you some results, and point out directions for future work, because we really feel there is potential to do more stuff here, not just identifying lamp poles, using our approach. And conclude with a summary and discussion. All right, roadway lighting. This brings me back to Peter Walsh's talk. He had this huge map of nighttime lighting in the world. So yeah, we have a lot of light poles, especially in US and North America, right? Just US alone has like millions of light poles out there. New York City has about 260,000 of them. And over the years, they are typically ignored and antiquated infrastructure. Old technology also consumes a lot of energy. For example, let's look at California. When it comes to California's lighting electricity bill, 22% of it are actually coming from street lights. In 2014, 19% of the country's energy budget went into lighting itself. In addition to being major components of our electricity bills, street lights are also difficult to maintain, right? If you look at Los Angeles, which is currently undergoing a major revamping of their street lights, but back in 2008, they were getting something like 70,000 calls on their 311 system. So I don't know if you guys know about it. There is a system called 311 where people can call up and log complaints about their civic infrastructure. And as an aside, it's great to just look into the data to understand how people interact with these civic infrastructures. So yeah, I mean, conventional lighting system is difficult, it's expensive to maintain, and they also have a pretty high failure rate over the life cycle of the project, right? So this is or was the state of the art, and cities have realized this. So for example, in 2008, there is something called the American Conference of Mayors, and about 288 mayors were interviewed, and the so-called light-emitting diodes or LED technology is on the top of their agenda when it comes to energy efficiency. So what are cities doing? They are essentially replacing their old light points, which could be high-pressure sodium or other things that I'll show in the next few slides, with light-emitting diodes, right? And why do they want to do that? When we look at it, converting street lights to LEDs gives you the most bang for the buck when it comes to energy saved per dollar invested, right? Not only that, they are they age very well, in the sense over the lifetime of the contract, the failure rate is extremely low. And consequently, across the country and even across the world, there is a huge surge in interest among the cities to revamp their roadway lighting, right? But I would argue that this process has been anything but smooth, right? So for example, Chicago came up with this request for information. I don't know if you can see this in the back, but Chicago is actually planning to revamp their light points, and as part of this request for information, they are asking for responders to come up with a system to inventory their street lights, right? The point that I'm trying to make here is one of the most important impediments to this LED conversion process is cities not having accurate inventory about their light poles. What do I mean by inventory specifically? They don't know. They want to know rather where exactly are the light poles located, what is the type of the lamps, what is the fixture type? Is it a decorative light pole? Is it a shoebox type of a fixture? Is it a cobra head, etc., etc.? And other things like height. What is the power consumption of the current installation out there, and things like that. And when they don't have accurate inventory and go ahead and still perform LED conversions like what happened in El Paso, they run into problems like being overcharged by the contractor and all sorts of inefficiency issues. Right? And then there is the curious case of San Diego, which has inventory, but turns out there are two departments in San Diego called the Street and Lighting Division and the Environmental Services Department, and their inventories of the street lights differ drastically. Right? Specifically when it comes to lamp types, the two departments seem to differ when how many lamp types do they actually have. So given the overall inventory problem during the summer of 2015, we decided to focus on one particular aspect, that is trying to understand what is the lamp type. Right? And here are some of the common lamp types that are shown there. High pressure sodium is typically used a lot in the US. Of course, there's a lot of light emitting diodes also. So we wanted to understand, given the location of the light poles, that's another problem to be solved. What is the type of the lamp that goes into the fixture? And so it's not that cities are not solving it today, right? What are cities doing? People actually go out there during night times or maybe during daytimes to read the labels on the shoebox. And by reading the labels, they are inferring the lamp types in a completely manual fashion. So obviously it's very expensive. It's not at all scalable because people actually have to walk and do it, and it's error prone, right? So we wanted to do it in a slightly different way, and people have been trying out this vehicle mounted sensing approach, as we all know. And the whole idea was to come up with a sensor box, put it on top of a car and drive around and collect data that will help us solve this lamp type identification problem, right? The premise of all this work is, of course, that different lamp types have so-called spectral signatures. That is, because of physics of the lamp itself, the spectral power distribution is a signature for that lamp type. We were mainly focused on 4 lamp types: high pressure sodium, LEDs, metal halide, and mercury vapor. And as you can see here, on the x-axis is the actual wavelength, and the y-axis is the count reported by the spectrometer, which is a proxy for the power content at that wavelength. And at least for these 4 lamp types, you can see that the signatures differ quite a bit. Yeah, I mean, one vendor's product might differ a little bit from another vendor's product, but when it comes to the overall morphology, given the application of roadway lighting, these spectra are a good enough distinguishing feature, right? So the whole idea was to come up with the sensor box that captures these signatures as we drive around, and once we get these signatures, we could classify them offline, and even visually you can see that the signatures are really distinct from each other. So we wanted to design the sensor box, and what are the functional requirements? Firstly, it should help us identify which light pole we just drove by, right? So at least give us an indication to which light pole does this current spectrum correspond to. Of course, be able to capture the spectral signatures in a reliable fashion. That is, you could be driving at different speeds. Light poles are typically dimmed in different areas, so it has to respond to different light intensities. And most importantly, it has to be rugged. It should just not fall off the car, things like that. So this is what we came up with. It's a polycarbonate enclosure with, first of all, you see an illuminance sensor there and a GPS receiver. This is a satellite-based augmentation system-enabled receiver. It's not very fancy. It does not have differential GPS capabilities. And of course, we have a spectrometer. How does a spectrometer work? It has an optical fiber which has a lens at one end. The light goes into it. The light is split up into different wavelengths, and these different wavelengths activate a CCD sensor, which reports an intensity or a count of number of electrons. Again, a proxy for the power content at that wavelength. So yeah, I mean, all of these three sensors were managed using a Raspberry Pi, and this polycarbonate enclosure has magnets underneath, so you can just throw it on top of a car, and it has tape. Don't worry, it won't scratch your car, and you can just drive along with it. Back in 2015, this is what it used to look like. It's not as clunky as anymore. There's not a whole lot of duct tape going on. We have a tripod for the antenna. But this is a typical usage scenario of the box. Right. So we wanted to validate this, right? So the whole idea being, as I drive with this box on my car, I can collect the spectral signatures. At least the morphology, the shape of the spectrum, needs to be preserved by the box. So here is Shengrong actually performing an experiment. This is a stretch of road in our New York campus. We were in New York back in 2015. Now we are in Cambridge with LED light poles. So we were able to set up a grid on the road and put the box on a trolley to mimic the height of the car, and just move the trolley along the road and place it on different points on this grid, which was laid out on the road, and measure the spectrum in a stationary fashion first, then just move it along at a walking pace, collect it, and eventually put it on top of a car and drive around. During this whole process, two parameters were kind of, we found that these two parameters are important when it comes to using spectrometers. Firstly, the diameter of the fiber that is used to collect light, and finally the exposure time, how much time do you expose the fiber to the light for collecting each sample, right? And for most typical roadway lighting applications, at least when it comes to residential areas, 1000 micrometer fiber and a 500 millisecond exposure time is enough, and we were able to establish that at least the box, when driving around, preserves the shape of the spectra reasonably well. A small point actually, so there is a small peak at around 900 nanometers that's caused by the human who is present around this box. That's due to the heat of the human being around it. So what do we do with this? First of all, how does each spectrum look like? It's just a 2229 values, which essentially have power between 350 nanometers and 1023 nanometers. And we were, as you can see, each lamp type has a fairly different spectral signature as compared to the others. So we were just able to set up a small library of 25 representative samples. And this was, of course, done with the help of domain experts. And we tried out the nearest neighbor algorithm, right? That's the simplest thing that you can do here. And turns out cosine similarity metric worked pretty well for us, right? We also tried out simple things like Euclidean and Manhattan distances, which don't give as much accuracy. So what does the classifier do? It just takes the unknown sample, removes the fake peak, scales it down, and then computes the nearest neighbor in the library, right? And associates this. For example, this is a high pressure sodium lamp. It's scaled down already, and it would actually, the nearest neighbor in the library would, with a high success rate, be a high pressure sodium. Right, so here are some typical results, right? So these are confusion matrices, 4 types. We were mainly interested in recall rates because cities want to know if they have 1,000 high pressure sodium lamps out there, is our system able to report back those 1,000 lamps? We could also do things like precision and F-scores out of it. One interesting thing is we have added a 5th type here called mix. I'll talk about it in the next few slides. And this is where we were actually driving around people's front yards and trying to get into. So this involved actually 4 field trials. And as I mentioned, cities don't really have a good inventory, but turns out the small town in Rosendale, New York, did a survey, manual survey, and they had about 100 light points in their village, and that gave us an opportunity to actually go there and drive with the system and compare it to the ground truth that was established by the town. Right? And other places like our surrounding areas in New York also gave us a chance to sort of see what happens when you have a diversity of lamp types, right? So you can see this one road actually passes through commercial and business areas, and they actually have a good enough combination of high pressure sodium lamps and mercury vapors. Moving forward, right? What can we do with something like this? And that's the more interesting question. First of all, we need to address the problem of these mixed spectra. What are they? They occur when two different lamp types are right next to each other, because of which the data that is captured by the spectrometer is essentially a superposition of two different lamp types. So here you have a high pressure sodium lamp, which if it is located right next to an LED, what you observe is this mixed type. And this is not very difficult to classify, but it's not currently handled by our system. They occur very rarely, so we didn't think it was worth working on this problem. But it's not very difficult to use a least square error kind of approach to solve this problem. After identifying the lamp types, what do we want to do? We want to actually feed it back to the original problem of large-scale LED conversions. We want to understand if we can use such a system to actually visualize the light poles. Many cities like Cambridge, the city where I work in Massachusetts, are doing a very good job of helping people visualize their current lighting assets, and also help them track conversion projects. And finally, there are many interesting applications of spectral data that are possible. That's what we feel. In addition to helping us understand what the lamp types are, we want to know if we keep doing this in a recurrent fashion, if we sort of keep collecting every 6 months or so, and as the lamps age, what happens to these spectra, right? There's a lot of talk about blue light hazard. So there, you can actually understand from the spectra what is the blue light content in the spectrum. And that's also, so the point being, this system can be used to collect spectral data in a scalable fashion. What do we do with that spectral data is something that the community could investigate. Finally, I'll just leave this open. This is the summary of the slide. So lamp type surveys are needed by cities. They are not doing it very well today. Vehicle mounted spectrometry is one way to go about doing it. So we have worked out the engineering parameters that are needed for the spectrometer to work. These signatures are really different from each other, so classification is not a problem as long as your system can collect reliable, good quality data. And there are many interesting things that we can do with something like this. So with that, I open up for questions.